10, 12, 5, and we're continuing on this idea of the z-scores from last time. You remember we looked at the z-scores for the marathon, and we had to convert them into the same units. We had to do minutes, and that was one idea, which kind of was fun because it tied in two ideas that we've been looking at in this unit, or in this semester. What they do here is they talk about, we've seen that male heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Suppose we are interested in the percentage of men with heights below 80 inches. So just for your own kind of putting your head around it, 70 inches is 5'10", right? And so 80 inches would be like 6'8", right? So that's pretty tall. And so we want to know most men, we're assuming probably most men are under 6'8". But we want to know the percentage of men with the heights below 80 inches. Well, if you go ahead and compute the z-score for that, you get 2.5. And we remember last time from our normal model that it was centered at 0, and we had 68% of the data is within 1 standard deviation. 95% is within 2 standard deviations, and 99.7% is within 3 standard deviations of the mean, right? Well, the problem, so this is -1 and 1, this is -2 and 2, and this is -3 and 3. The problem is if we wanted to know the percent to the left of 2.5, so if we wanted to know the area, all that area up to 2.5, we can't quite use any of those rules exactly. We can have an argument. We can say, well, we know for 2% it's 97.5 of the data is to the left, so it's probably a little more than 97.5, but we don't know what it is exactly. So what you do is you do calculus, and you integrate the area under the curve of the normal distribution. So you want to get to 2.5, and this is e to the square root of mu over sigma minus x over sigma dx. It's a little scary, right? Not this class. Okay, it's not even a class. It's not even a class that you want to take. And actually, I'll just tell you, I just threw this out here. I may actually be a little bit wrong on this formula, but it does have an e in it. It does have mu and sigma and all this kind of scary stuff in order to figure out what the area under that curve is. Well, once they figured out that that was the formula, what they did is they said, forget that. We're not going to have to do that formula every single time. We're just going to make a table that'll give you the values. And then we did the calculation for you. So they took the scary away, and they put it on a table. And here is the table that will help you get percentiles for specific values that are not on the 68, 95, 99.7. Okay? So, for example, the 2.5, you just come down to your z-score of 2.5. I already highlighted it. And you will see that 99.38% of the men will be to the left of 80 inches, or to the left of 2.5. Does that make sense? Because 2.5 is the z-score that's associated with the 80 inches. And this percentile means the area to the left or the percent below the percent to the left. All right, so it's pretty fun. Let's look at an example now. This is like the first problem in your homework. It says, use the table below to find the percentage of data items in a normal distribution that lie below and above a z-score of 0.3. So I hope this particular unit, or this particular section and the one before it, should be motivators for you to take a statistics class. Even if you go on to graduate school, I would expect you're going to need, even if you don't need any more like calculus or college algebra or anything like that, you're probably going to need a statistics class. And having this unit, having these notes, is going to help you through the first sort of ideas with a normal model. So you're going to be really glad that you've thought about this before. It's going to give you a heads up on some of the thinking in a course on statistics. So the first thing I would always tell a student to do in a statistics class is to make a picture. So we have a normal distribution with a z-score of 0.3. Now, when you're dealing with the z-score, that means the standard normal model. With everything is standardized, the mean is 0. Because remember, to get the z-score, you do data minus mean divided by standard deviation. So if you did mean minus mean, that would be 0 over standard deviation, which would be 0. So for the standard normal model, the mean is just 0, and then 0.3 is, I don't know, somewhere about right here. So we want to know the percentage of the data items in a normal distribution that lie below 0.3. So what they're really asking for is what is the area under this curve to the left of 0.3. Well, the table gives you exactly that answer. So if you look at your table and you go to the 0.3, you will see 61.79 is the percentile or percentage of data to the left of 0.3. So 61.79% is the percent of the curve, or the amount of the curve that is below to the left of 61.79. Now, if you want to go 0.3. If you want to go to the right, remember underneath the curve, the whole thing is how much? 100%. So the area to the right is going to be 100% minus 61.79%. So if you know from the table the area to the left is 61.79% of the model, this then is just going to be 100% minus 61.79%, which you can type in your calculator, 100 minus 61.79. You get 38.21 is the percentile, or to the right. Or it's actually not the percentile, that's an amount above. The percentile always refers to the amount below or to the left. Okay, let's do another one. It says, use the table below to find the percentage of data items below and above a z-score of negative 1.6. So again, I'm going to tell you to make a picture, even though you may feel like you've got this figured out. We'll put the 0 here because we're dealing with the standard normal model. Negative 1.6 is somewhere here, and we want to know the data items below that, which means we're looking for the percentage of the area in the curve that is to the left of negative 1.6. And if you look at your chart, it's right there, 5.48 is the percent of data items that lie below that. So you do 5.48. And so then clearly, to get the amount above, you're just going to know the whole curve, under the whole curve is 100%, so this is going to be 100% minus 5.48%, or 5.48, which is 94.52. Now, I need to take a moment to tell you that when I teach this class, if I were teaching this class in statistics, I don't teach it with the tables. I think tables are kind of like old school. I say there's probably a calculator app that's going to do this for me, or something on the computer that will find these percentiles for me and actually probably do a better job, be more accurate. And that is in fact true. And so in the spirit of that, I'm going to show you the buttons on the TI-84 and how you get it to give you the area. So you can't do your homework this way, because the homework you're going to want to use the table, because there's some rounding that's going to occur and actually makes the tables less accurate than what the calculator gives you, but the computer won't grade your answer right, even though it's more right. You know what I'm saying? So I'm just sort of giving you extra information for to take with you, so that you know that this is not the only way. The table is not the only way to do it, and the TI-84 is not the only way to do it. You can do it in Excel. You could probably Google it and figure it out as well. So on the TI-84, you're going to use this. You're going to type the second button, and then you'll see the word. It's the VARs, but it's distribution is what you're looking for. It's a blue and it's distribution. So do y'all see that second distribution? It's next to the clear, yeah. And this is a word that we're going to say the normal distribution is a cumulative density function. Okay, it's a type of function. It's a CDF. There's also a PDF. Right now we're just going to talk about the CDF. We're going to accumulate up. That's what it's telling you. It's adding up all the area up to a particular value. So it's the normal CDF. And so you're going to choose that one. So it's normal CDF. And the syntax on these, depending on what kind of computer you're using, can be different. So this is specific to the TI, but they're pretty similar. All right, and so then it takes you back to the home screen, and it gives you this normal CDF command with a parenthesis. Oops. If you select it, it takes you back there, okay? And it's waiting for some input. Now, what it likes is the lower Z, or the lower data value, then the upper data value, and you have to put commas in between, and then the mean, and then the standard deviation.
In that order?
In that order with commas in between. Now, what's kind of weird is that when you're just looking for all of the area to the left, you're not, when you're looking for all of the area to the left, you don't have a lower data value, right? It's just all of it. So on your calculator, you can't just tell it, you have to just make up a number. So just pick a number that's really far to the left, like negative 1,000, certainly way to the left. So we'll just pick a number that's really far to the left, like negative 1,000. And then the upper data value is where you want to stop, which in this case is the negative 1.6. And then the mean for the standard normal distribution is 0, and the standard deviation for the standard normal distribution is 1. And then when you come in on your calculator, you can just do, now be sure to use the negative and not the minus. Negative 1,000, comma, negative 1.6, comma, 0, comma, 1. And it gives you pretty close, 0.0. If you multiply that by 100, then you get the answer that was on the table, rounded. If those of you that tried it on your calculator, did anybody get an error, or did you get this? If you got an error, the one thing that you can do wrong sometimes is that you use the minus sign instead of the negative sign. Okay, and then it turns out if you wanted to get the other side of it, if you wanted to get the area from negative 1.6 to like positive infinity or really big numbers, you don't have to do 100 minus. You could actually call that same command up again, the normal CDF command, and you could change your lower limit then would be the negative 1.6, and your upper limit would be like 1,000 or 10,000, whatever you want to do. And then that's how you'll get the 94.52. But you could also do 1 minus. So just something interesting on your calculator. Okay? And in a minute, we're going to look at between two z-scores, and that's actually very easy to do on your calculator as well. You just put the lower value in, and then the upper value in, comma mean, comma standard deviation. It's kind of fun. The only thing you can run into is that sometimes they're just a little bit off on the rounding, and the computer might give you a hard time with grading it. So we'll stick with the tables. Use the table below to find the percentage of data items in the normal distribution that lie between 0.8 and 2.3. Okay, so you have to do a little bit of thinking here. I always like to draw a picture. 0 for the standard normal model is your mean. Now we've got 0.8, which is about here, and 2.3, which is about here. Okay? And we want the area in between. This is kind of if your table will only give you the area to the left, then you're going to have to do some thinking. For example, if you look at 2.3 on the table, you will get all of this yellow area right in here. Right? But you don't want that. You only want the area between 0.8 and 2.3. But if you look at 0.8 on the table, it'll take away, it'll show you all the area to the left of 0.8. So if I put 0.8 in, then I'll have this. So if I just subtract the percentage below 2.3, the percentage below 0.8 from the percentage below 2.3, I will get the correct answer. All right, so you kind of do the larger z minus the smaller g. So I'm going to do, I'm going to do percent below 2.3 minus percent below 0.8. So the percent below 2.3, I come up to my table and I just get that number, which is 98.93. And the percent below 0.8 is 78.81. So I'm going to do 98.93 minus 78.81. So 98.93 minus 78.81. And we get 20.12. And that is our percent in between that. Okay? All right, now let's look at an application problem. It says, the results of a certain medical test are normally distributed with a mean of 127 and a standard deviation of 11. Use the table to find the percentage of people with readings between 118 and 136. Okay, now the trick here is that you've got to get if you're going to use the table, you have to get the 118 and the 136 into z-scores. And then you can use the table, because the table deals with z-scores. Now, the beauty of the calculator is that you don't. Remember, it goes comma mean, comma standard deviation, so you can actually just go 118, comma 136, comma 127, comma 11, and you're done. But if you're doing it by hand, you've got to use the tables. So it just kind of depends on how you want to approach it. So let's first know that the z data value is equal to the data value minus the mean divided by the standard deviation. So for a particular data value, the z-score tells you how many standard deviations you are away from the mean. So for the 118 data value, you do 118 minus the mean, which is 127, and you divide by 11. So if we do that, and do that in parentheses on your calculator. And so you get negative 0.81 repeating. Okay, and so what that's saying is that 118 is about negative 0.8 standard deviations away from 127. It's not even a whole standard deviation away, it's just a little bit. Okay, it's 80% of one standard deviation. Right, now notice that they tell you to round to the nearest tenth right away. And so that's where this rounding, and then with the table, things get kind of touchy-feely pretty quick. Like, they're not exact, but statistics is not an exact science. It's just kind of there to give you a basis for some numbers to make good judgments, but it's not supposed to be dead on. All right, now the z-score for the 136 is going to be the data value, 136 minus the mean, 127, divided by 11. When you do that one, you will see, I can just edit my previous entry here on my calculator. You will see that you get 0.8 again. All right, so we have negative 0.8 and positive 0.8. Okay, so negative 0.8 and positive 0.8 are our readings that we see here on our table. What do we do with those? Well, I always like to draw a picture. So there's my standard normal, zeros at the middle, and I'm going to put negative 0.8 and positive 0.8 on either side of it. What I'm looking for is the area in between negative 0.8 and positive 0.8, because that's the people with the readings in between there, 118 and 136. So now I'm just back to the same idea. I'm going to find the area to the left of 0.8, which is going to be on my table. That is the 78.81. And then I'll find the area to the left of negative 0.8, which is the 21.19. And then when I subtract them, that will give me the area in the middle. Okay, so I'm going to do the percent below 0.8 minus the percent below negative 0.8. So looking at my chart, that's 78.81 minus 21.19. So 78.81 minus 21.19. Oops. And I get 57.62. So if 57.62% of the people that take this test, this medical test, will be within 0.8 of a standard deviation from what is the mean or what is the average. So probably that kind of tells you about what you can expect if you were to do the test on a lot of people. And then you can see that if a person has 150 as their reading, you might be suspicious or worry they may need to get some treatment or something, depending on what you're dealing with. Okay, just for a second, if I were to do this with my calculator, I don't even have to do any of that z-score stuff at all. I can just do the lower data value, which was 118, comma the upper data value, which is 136, comma the mean, which was 127, comma the standard deviation, which was 11. Now, the answer that it gives me is not going to be exactly the same as the answer that I got when I used the table. And the reason why is because the calculator is actually more accurate than the table. When we found the z-scores, you remember it was 0.81, 81, 81. Well, the calculator remembers all of that and handles all of that rounding, but your table didn't. So while it's not going to help you complete the homework, it is, in fact, still a quick way to get the answer if you're just trying to know, if you're just trying to get an idea of it. So, most of the time in statistics, they understand the different computational errors that you can get, and so it's not within a couple percentages. It's not that big of a deal. Okay, this is a common question. I don't know if you have children or you have, nephews and nieces and that sort of thing, and little babies when they're born. You always kind of want to know how they compare in size to, their counterpart babies. And they have these growth charts, and you always want the boys to have, really high percentile in height, or mostly when they do the height and weight, what the doctors were looking for is for them both to be about the same. Like if you're in the 90th percentile in height, that means you're taller than 90% of all the babies. Maybe you're 18 months old, and if your weight is in the 50th percentile, that would be a little bit disconcerting. You may be actually too thin, because if you're in the 90th percentile in height, you probably need to be about in the 90th percentile in weight too. Now, maybe they recalculate and they say a healthy weight, because right now, I don't know if you've done a lot of reading, but they say that children are getting more and more to where more children are not at healthy weights. So if you have that chart where you're in the 50th percentile, you may actually still be, if you're using a chart where all the babies are overweight. It's like a fat baby chart. They have the fat baby chart.
Those things are so, I don't pay attention to them.
Yeah, they make me nervous though. It makes you like, I don't know why you should start comparing your child, at the moment that it's born, to all the other children.
The thing is that it depends on various things. I know, for example, I got a great nephew. He was a butterball.
And now he's skinny. Yeah.
And as soon as he started walking, he just covered everything. I didn't even recognize the kid when I saw him. When he started walking.
I think that doctors take that into account too. I don't think they just kind of use it as a guide to make sure there's not something really crazy going on. Because probably if you're in 90th percentile in one and 20th percentile in the other, that there is going to be some concern there that something's not going well. But anyway, it is just for a guide. All right, so let's look at this. We've got the weights of a group of 18-month girls are normally distributed with a mean of 24.6 pounds and standard deviation of 2.4 pounds. Use the given table to find the percentage of 18-month-old girls who weigh more than 25 pounds. Okay, so we're going to need to get the Z data for 25, because that's going to be our Z-score for 25. So that's the data value, which is 25, minus the mean, which is 24.6, divided by the standard deviation, which is 2.4. So we come in here on our calculator, and we do 25 minus 24.6 divided by 2.4. And you get 0.16. So remember, they want you to round your z-score to the nearest tenth. So that's actually going to be 0.2. So this is equal to 0.2. So that's my z-score. Now I want to know the percentage of girls that weigh more than that. So I'm going to come in here on my model, centered at 0. I'll pop 0.2 about right here. What I'm actually looking for is the ones that are to the right of 0.2. But the table tells me the area below 0.2 or to the left. So if I come in on my table and I look at 0.2, that tells me that 57.93% are on that side of the table, or on the left side, if 0.2 is kind of your break point. So in order to get this number, I'm just going to do 100 minus 57.93. And of course, those are percentages. So it's 100 minus 57.93, which is 42.07%. Okay? So that's kind of fun. All right, now this question is just kind of put here to help you, when you hear the word percentile, help you understand what it means. Percentile means what percent of the population is to the left of whatever the data value is. So it says the table to the right shows selected ages of licensed drivers in one country and the corresponding percentiles. Find the percentage of drivers who are younger than 75. Well, if you're 75, you're in the 98th percentile, which means that 98% of the drivers are younger than 75. Okay, so I know that was a tough one. But maybe you've heard the word percentile before and now you know what it means. Okay. The placement test for a college has scores that are normally distributed with a mean of 450 and a standard deviation of 90. If the college accepts only the top 16% of examinees, what is the cutoff score on the test for admissions? Okay, so now we've switched our thinking, and we have to go completely in reverse. All right, we have to do like a teeny weeny bit of algebra. All right, so let's think about what we have. I always like to start with a picture. We're looking for the z value that is associated, so we're looking for the z data that's associated with the top 16%, right? When we know that, and then once we get that z data value, we can use the mean and the standard deviation to come up with the data value, because we also have a formula that is that the z data value is equal to the data minus the mean divided by the standard deviation. All right. So let's see if we can't figure out what that z data value is. Well, on the chart, and this is kind of an unfortunate example because you probably remember from the 68, 95, 99.7 rule what that z data value is. Maybe you do. The one that has, you might remember that 68% of the data is within one standard deviation, which leaves 16% on either side. So it is 1. But say it was if it tweaked the percentage a little bit. Well, what you're going to have to do is figure out what this area is first, and then look at your chart and find the area that's closest to it with the corresponding z value. So this area, of course, is going to be 100% minus 16%, which is 84%. And then you have to look at the chart, and you're going to pick the percentile that is closest to 84%, which you should see is 1. Okay? And so this is your z data value, 1. So you're going to put 1 in for the z data value, and you're looking for the actual data, the test scores, minus the mean, which is 450, divided by the standard deviation, which is 90. So here's where the little teeny bit of algebra comes in. You've got to solve for data. All right, so it's data minus mean divided by standard deviation. So what's the first thing that you'll do? Good. The first thing you'll do is multiply both sides by 90. So you'll have 90 is equal to the data minus 450. And then the next thing you'll do is add 450 to both sides. And so 90 plus 450 is 540, right? And that's your answer. So students with a test score of 540 or higher will be selected for admission into the college. Okay? So that's the cutoff score. I was just looking at that yesterday for A&M. If you're not in the top 10% of your high school graduating class, then you have to be in the top quarter and have an SAT score of at least 1,300 with 600 on each of your at least 600 on each of the verbal and the math. So it's quite strenuous to try and get in then if you're not in the top 10%. They've changed that. And then I guess UT has changed it to where they don't even, it's not automatic acceptance for the top 10%, it's the top 8%. And then everyone else. But I think the idea was that's better because it used to be that a lot of people would be like in the top 11% or 12% and they couldn't get in. But now they're saying if they only have to accept top 8%, then they have more room to accept other people. Mm-hmm.
How can they just accept the top 8%? Because it was a law. I thought that they had to accept.
I don't know how they approved it, but it's just what I've heard. I'm not exactly sure how they got it passed. It did used to be a law, and I do think they've kind of cut back a little bit on it. Okay, determine whether the statement below makes sense or does not make sense, and explain your reasoning. So let's try to think about the statement first before we look at all the answer choices. Because I'm using a table showing z-scores and percentiles that have positive percentiles corresponding to positive z-scores and negative percentiles corresponding to negative z-scores. No. Percentiles can't be negative. A negative z-score just means you're to the left of the mean, but there's still going to be area, right? The percentile is kind of the area. So that doesn't make sense to have negative percentiles. So we get to pick from either A or C, because it can't be make sense. And it looks like it's going to be A. The statement does not make sense because although negative z-scores are possible, negative percentiles are not. So that's just a little question there. Okay. The results of a certain medical test are normally distributed with a mean of 122 and a standard deviation of 20. Convert the given results into z-scores and then use the table below to find the percentage of people with readings between 148 and 168. So this is the same type of question that we did a few minutes ago. We're going to need to find those z-scores for 148 and the z-score for 168. And then we're going to want to find the corresponding percentiles and subtract them. So the z-score for 148 is, remember it's the data value, which is 148, minus the mean, which is 122, divided by the standard deviation, which is 20. So I'll do 148 minus 122 divided by 20. And remember to use parentheses if you're doing that in one line on your calculator. So you get 1.3. Now the z-score for 168 minus 122 divided by 20. If you've got your thinking cap on, you're one standard deviation beyond 148. So you might expect this number to be 2.3, but you can check and see so that you are in fact, because you're 20 more, which is one standard deviation. And it is 2.3. Okay. So we have a normal model. And it's a standard normal model, meaning it's centered at 0. We've got 1.3 and 2.3. And we want the area between those two to z-scores. So if I look on my chart, it will give me the area below, or the percentile below 2.3 as 98.93. And then if I look on my chart, the area to the left of 1.3 is the 90.32. And so if I want to get the area in between, I just subtract the 98.93 minus 90.32. And so 98.93 minus 90.32 is 8.61. Okay? So this is just your first little taste of playing with the normal model.